We'll discuss a very important concept of relating rational functions and polynomials.
I'm Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll understand the connection between the rational functions and the polynomials. This transition is very important to understand. We'll actually explore the graphs and the equations, relate them, to see how rational functions are related with polynomials. Well, very first thing is the definition of rational functions. A rational function, r of x, can be written as the quotient of two polynomials. So in the numerator, we have a polynomial. In the denominator also, we have a polynomial. However, since you cannot divide by 0, the denominator polynomial can never be 0. Now that leads to restrictions, right? Since you cannot divide by 0, we have some restrictions because of that. So this denominator equals to 0 results in two things. One, either a whole or a vertical asymptote. Moving forward, we will understand when do we get wholes and when do we get vertical asymptotes, and what are these? So this is one of our major activities in this particular video. So we come to know whether there are wholes or vertical asymptotes by simplifying a rational function. Just as in fractions, you cancel out common factors in numerators and denominators, in rational functions also, the polynomial factors will be cancelled to simplify. So we simplify rational functions, and once we do that, we come to know whether we have a whole or a vertical asymptote. Perfect? Now let us look at the graph on the right hand side. It seems to be a graph of a parabola, a polynomial. Perfect? Actually, it is not. If you notice carefully, it has a point here which is not in the domain. We call this point as a whole. In this video, you will learn how some rational functions can simplify to polynomials. They will, however, have a very important difference, that is, in polynomials, the domain is all real numbers, but in these rational functions, there are some restrictions, and mainly because the denominator d of x could be 0. That leads to restrictions. Well, if after simplification you get a polynomial type of a graph, it means that restriction is because of a whole. So we'll explore the wholes in greater details with the help of 4 examples. Now these 4 examples are unique since they expose you to different types of polynomials one by one. So stay with me to understand this topic, how some rational functions can be simplified to polynomials, and we look into their graph and the characteristics of these graphs. Here is our question number 1. We are given a function f of x as equals to 2x minus 6 divided by x minus 3. We'll identify the coordinates for wholes, x-intercept, y-intercept, domain range, and sketch this particular function to really understand it. But well, let's begin first with the function itself, which is f of x as equal to 2x minus 6 over x minus 3. So I can factor 2 from the numerator, which will result into the other factor as x minus 3. So now you see that we have x minus 3 in both numerator and denominator. Now these factors can be cancelled. That is what I meant by saying that, the common factors can be cancelled. So to begin with, we had 2x minus 6 over x minus 3. Definitely denominator cannot be 0. So x is not equal to 3. Since the value of 3 for x will give you in the denominator a 0. You cannot divide by 0. So that is a restriction. Now, in the second stage, when we simplified the rational function, what did we see? We see that this factor, which gave a 0 in the denominator, cancelled. So that results into a whole, right? So that means we have a whole at x equals to 3. You get the idea. So you literally get f of x as equal to what? Let me rewrite this simplified form, which is a constant 2. However, we have a restriction that x is not equal to 3. We have to write this restriction. You get the idea. We have to write this restriction so that we can say it is really equivalent to the rational function. Is that part clear to you? Now we'll just sketch this graph and look into some more parameters. So let's move on to a fresh page. So what we did just now was that we wrote f of x as 2 times x minus 3 over x minus 3. We simplified by cancelling the common factors, and we said that x is not equal to 3. Perfect. So it is a constant. So we also saw, since this factor cancelled, so whenever a factor cancels in numerator and denominator and leaves nothing in the denominator, it creates a whole, right? So we have a whole. So now, clearly, there is a whole at 2, right? I mean, whole at 3, whose value could have been 2. So if I have to sketch it, how do I sketch it? Let me just show you that sketch also for better understanding. So we see that it cannot have a value of 3, but it is always 2, right? So it is a constant function, which is kind of like this. So it is a constant function, which is kind of like this. And here we are representing open circle, which represents the whole. The location of this open circle will be what? Can you tell me? Well, the x value has to be 3, right? And the y value, we know we have y equals to 2, correct? So this is 2. So we have a hole here whose coordinates are 3, 2. You see that? So that is what we meant. It is a constant. Constant is also a polynomial. Perfect. So we see that in this particular case we have a hole, and the location of the hole is 3, 2. Now this graph does not have any x-intercept, right? So none. Has a y-intercept which is at y equals to 2. The domain of this function is x belongs to real numbers, and the range of this function is y is equal to 2, right? So only one value, and the graph is before you. You get an idea. So some rational functions can be simplified, and they look like a horizontal line as shown here. Amazing, right? Let's move on and see the second question. Now in the second question, we are given the function f of x as equal to x squared minus 4 over x plus 2, right? So we are given that the function is equal to x squared minus 4 over x plus 2. You could factor the numerator, write it as the product of x plus 2 and x minus 2, correct? Now you see that x plus 2 is a common factor in both numerator and denominator, and therefore that cancels, leading to a polynomial, and the polynomial here is x minus 2. Makes sense? Of course, x cannot be minus 2 since that will give a 0 in the denominator, and so we have a restriction here, and that is that x is not equal to minus 2. Do you see that? So this factor which cancelled led to a whole, right? So we are now writing that the function f of x is indeed equal to x minus 2. However, x is not equal to minus 2. So at minus 2, we have a whole. So if I plug in the value minus 2 here, what value do we approach? We write it like this. If x approaches minus 2, we cannot be there since, this function cannot be at x equals to minus 2. But we can be very close to that value, correct? So as x approaches minus 2, the function f of x, which is simplified as x minus 2, approaches minus 2, which is minus 4, correct? So we know that the whole is at minus 2 x value and minus 4 y value. Do you see that? Perfect. Now, let us sketch this function also and try to understand this rational function which has been reduced like a polynomial, a straight line x minus 2. So once again, we wrote this particular function f of x as x square minus 4 over x plus 2 and simplified this to x minus 2 where x is not equal to minus 2. So that is like a polynomial, right? So I'm always using the word like a polynomial since there is a difference, and that is in this there is a restriction. In polynomials, there are no restrictions. Perfect. So if I have to sketch this particular graph, then how am I going to sketch it? Well, it is going to look like a line going like this, correct? However, on this line we have a restriction, and that is at minus 2 we have a hole. So I am deliberately drawing it bigger just to give you an idea that this point is not in the domain of the function. So at x equals to minus 2, we have a hole whose y value is minus 4 as we found just now, correct? So that is the hole, right? Well, so we have found that in this particular case where the restriction is that x is not equal to minus 2, the hole is at minus 2 minus 4, right? The x-intercept in this case you can find since we wrote f of x as indeed equal to x minus 2, right? Where x is not equal to minus 2. X-intercept is when the y value is 0 and y-intercept is when x value is 0, correct? So let's find the x-intercept. This is equal to 0 for x equals to 2, right? So that gives you x equals to 2. So the x-intercept is at x equals to 2, correct? And y-intercept clearly is given at y equals to minus 2, right? Which is f of 0, right? So we get 0 minus 2, which is minus 2. So y-intercept is at y equals to minus 2. As far as domain is concerned, we see that x belongs to real numbers. However, x is not equal to the whole position, which is minus 2. Makes sense, right? Now, as far as the graph is concerned, you see it looks like a straight line with a restriction, a hole at minus 2 minus 4, correct? So once again you saw that this rational function could be written as a polynomial, right? But there is a restriction, and that restriction is because the denominator factor cancelled, leading to a hole, right? And this time we got a straight line. Perfect. Now, let's move on and take the next question. So it is a question related in a word problem kind of a thing. Part C is determine a rational function that simplifies to a polynomial with domain x belongs to real numbers and x is not equal to 5. Describe what happens to the graph at x equals to 5. So open function for you. So you're saying that you have a function whose domain is something but not equal to 5. Clearly, we have the factor x minus 5 in the denominator. So if I have this, then we have ensured that x is not equal to 5. Makes sense? Now, since we have the other condition that it can be simplified as a polynomial, that means in the numerator also we have a factor x minus 5, correct? So that is how we could have a function. Now, to make it very simple, I could just multiply this with anything. It could be x, x squared, or any other polynomial, right? To keep things simple, I'll just write x here. You get the idea. So when I cancel these two, right? So in that case, what do I get? We get f of x as equal to x, and x is not equal to 5, clearly, right? X is not equal to 5 since there is a hole at this point, right? So we have a hole at x equals to 5. The y value will be what? We we see that it approaches 5, right? So 5 comma 5 is the location of the hole, which we'll show here in the diagram, right? So we have y equals to x line. So let me just sketch this line here. Do you see that, right? So we have this particular hole, right? So at 5, since the value is f of x equals to x, it is same, right? Do you see this hole, right? That's what we have. Now the important thing also which is being asked here is describe what happens to the graph at x equals to 5. So at x equals to 5, what we see that as x approaches 5, from the left side, right, which we write like this, we see that the y value or f of x also approaches 5. And when x approaches 5 from the right hand side, then also y approaches 5. So they are looking into one particular point from both the sides. Do you see that? So the limit is there, right? But it is this part which is not there in the domain of the function, which satisfies the given condition that x belongs to real numbers and x is not equal to 5. Makes sense, right? So what we see that from both sides we approach the same value, right? So both sides of hole we approach the same value. So whenever we say value, we are trying to say y value, right? The output, correct? So that is how we relate the things. So I hope the concept is now absolutely clear, right? So a rational function can be written as a polynomial with restrictions. Now here is the last question related to this topic. We are saying some rational functions simplify to polynomials. Here what we have done for you is we have given you the graph. So see, we started with the equations, then we developed an equation for the given condition. For the previous examples, we had sketched the graph, and this time we are looking back from the graph to the equation, understanding the whole concept, right? So part D, or fourth question related to our topic here is, write a rational function from the given graph, right? So if you see this graph, it looks like a parabola, a polynomial. However, you should note that there is a hole, and the location of the hole is at a minus 1, 4. So let me highlight this point first, right? So there is a hole at a, and the coordinates value is minus 1, 4, correct? And then we have a parabola whose equation we need to provide. So simply we could write this in factored form. We can say, well, this function f of x is equal to a times, we don't know what this a is, but we know the two x-intercepts. One is at 0, the other one is at 3. So we can write this as x times x minus 3. Makes sense? So we have this particular parabola. So that is the parabola. However, we have a restriction, and the restriction is that it cannot have a value of minus 1. So we need to divide this by x plus 1, correct? So, and also multiply by x plus 1. Now that results into the whole given to us. You get the idea? Which will actually cancel out and give us a function which will be a times x minus 3 over 1, right? Because they cancel away, right? You see that? They cancel away. So over 1. So it is just a polynomial. You see that? That is what we meant. And definitely in this particular case, x is not equal to the condition which is minus 1. Clear? So that becomes a restriction. This minus 1 is because of the hole shown on the graph of the function. Perfect? So now we see that at the hole you approach the same value from both the sides, right? So here the value being approached is 4. So if I put the value minus 1, so we say, well, we are approaching, we're not at 4, right? But we are approaching 4 when x is minus 1. So a times minus 1 times minus 1 minus 3, right? So that gives me 4 equals to a times, this is 4, right? So that means that a is equal to 1, correct? So we got the value of a as 1 itself, right? And therefore, I could write that the graph of this function can be written as an equation which is equal to a is 1, and therefore I could write this as x times x minus 3 times x plus 1, right, divided by x plus 1, correct? Which simplifies to x times x minus 3, where x is not equal to minus 1. Makes sense? So, with that, we understand completely that many rational functions can be simplified to a polynomial form with some restrictions. And these polynomials will always be represented by a continuous graph with a discontinuity, and the type of discontinuity is the whole. So let's try to understand all these things which we have learned in today's video. Well, the key points here are that the rational functions can be written as a quotient of two polynomials. I'm writing n of x in the numerator, d of x in the denominator, where the denominator cannot be equal to 0. The denominator equal to 0 results in wholes or vertical asymptotes in general, but when we are talking about reduction or simplification to a polynomial, they should result in wholes, right? So we've written, if n of x over d of x equals to a polynomial, then d of x has a common factor in n of x, resulting in a whole. Now, we also studied many properties of wholes. Let's summarize them. Whole is referred to as a removable discontinuity. We could actually add on another function to plug this up, and therefore it is also called a removable discontinuity. We'll look into more videos and more questions where this point will be highlighted. Factor in both numerator and denominator results into the wholes. Factors that cancel completely results in whole. This is kind of very important to understand. If a factor doesn't cancel, right, so we have x and x squared in the denominator. One of the x's gets cancelled, the other one doesn't, then there will be a vertical asymptote, okay? Now, more than one whole can exist. It's possible to have more than one whole. Function approaches the same value as we have seen in the whole here also. You can see that when you approach from either side, you approach the same y value. Rational functions can simplify to polynomials with the help of 4 examples. We have seen that, and we have seen it could be a constant function, a linear function, a parabola, or any function for that matter. Perfect. So I hope that brings us to a closure. You understand what exactly we mean when we say simplify the rational function. And does it look like a polynomial? Yes, it does. And it has a restriction, and always that restriction is a whole. And we have also seen different properties of wholes, which will help you moving forward. I hope that concept is absolutely clear. Feel free to write a comment, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.